That's how we're going now.
What? So here we're to do a material selection, outcome 4, which should look like that. So we're going to do that first, right? The tensile test, and then after we'll do the die penning on the back. Yeah. So here's our tensile tester machine, and I've got 2 samples to test, as machined and a normalised example here. And we're going to pull them apart till they break. So we can see where this one is broken, it's going to get a bit longer in the process. So we've got one in our machine here, it's not under tension yet. And what we're going to do is we're going to pull it, apply a force. We can measure the force on this digital reader here in kilonewtons. And we can measure the displacement change in length using this wee digital dial gauge. Yeah? So this collar, we can put this collar around the specimen, clamp it on, and that collar will change length here, like that. So when it changes length, this dial will change. So that'll give us for changing length. We could also use this vernier, attach it to here with a wee magnet, and that'll change. So one of the things, this is going to measure our change in length. So our original length, we measure the size off here, and when you put the collar right in, our original length is 50 millimeters. Yeah? The other thing we need to check, I'll put this collar in here just now. That's clamped on. And then you have to zero your gauge to make sure it's changing up to 0. Another thing we have to check is our specimen. We have to check what our diameter is. So, I need to check what the diameter is. From that diameter, you can work out what the cross-sectional area is. Yeah?
Close up on ground.
And you're going to need that because when we do this experiment, we'll start pumping, we'll say do 1 pump, take a reading of force, take a reading of extension. And you just do 1 pump, take a reading. Then you'll end up with the results of this example here. So a column for force, a column for extension. I'll do that for both samples, so it'll go on and on. And what you're trying to do with this results is, once you get your force readings, go into Excel, or you can do this by hand, is you can calculate your stress, and your stress is equal to force divided by area. So you have to work out your area of your sample getting tested. Make sure your force is in newtons and your area is in meters squared, and then if you divide them, you'll get your force in newtons per meter squared, or pascals. With your extension, similar thing, you can use that to work out your strain. Strain is equal to extension divided by original length. And as we said, our original length is 50 mils. Yeah? Once you get stress, a column for stress, a column for strain, you then draw a graph. Strain on the x-axis, stress on the y, and you should get a thing like this. So you'll get your elastic region, then your yield point, then your ultimate stress and your fracture stress. The gradient of this first part here, which is your elastic region before it starts deforming, is called your modulus of elasticity. And what you're expecting to get, there's a sample table at the bottom of the question paper. You need to produce a table for each specimen. So you'll have a gradient, modulus of elasticity, then the yield stress, the ultimate stress, and the fracture stress. And from this table you can make a comparison and comment on it. Other part here is you've got to sketch your apparatus, so you could take a picture of it and then take a sketch from that. Okay, thank you. We'll then take a video for that. We're not actually